Yes, but we're going now. Okay? We'll start from the current slide. Okay, now as we were talking about just before class started, last time we finished topic 3 and the lab 3. So we're starting now on topic 4 today, which is Newton's laws of motion. And I'm a little concerned because I know I had some stuff run off and I don't see it in my pile. Oh, I know what happened. I think I know what happened. Okay. And here's Shakina. I'll figure it out later. I think things got misplaced in my stack of papers. Okay. So today we're starting topic 4, laws of motion. It's a fairly long chapter. Okay. So I don't know if we're going, almost certain we're not going to finish in time to have a lab today. Pardon me? Yeah, it looks like we will be. Unless, well, it's a long chapter, and we'll see. If we finish the chapter and we want to just start on the lab and then pick up the rest of it later, it's bothering me now because I know I had the lab run off, but I just don't see it. I see something else I had run off at the same time, and I'm wondering now if she forgot to give me all of it. Okay. Here we go. Well, that's not as encouraging as I thought it was. It wasn't. Okay. They must be down in my office because I sure don't see them here. But we may not get to it today anyway, but this aggravates me. It's not where I thought it was. Nope. Not where I thought it was going to be, so. So if I need it, I'll have to go back to my office because it must be in there. I thought I put it in the right stack, but I must have put it on another pile. Okay, sorry about that. And let me get the people who have come in since. And, Monique, right. Is that everybody else who are here? I've called your name. You heard it. Okay. Okay, so we'll get going on the laws of motion. If we do finish the chapter and want to get started on lab, we'll do that and then finish the lab next time. Let's go. What we've done up till now, of course, the first one was sort of introductory type stuff. Then we looked at one-dimensional motion. Then we looked at two-dimensional motion. And now in this section, we're going to talk about all we've been doing so far is describing motion, okay, and talk about the general stuff. Now we're going to see why motion works, the laws that govern the motion. Okay? And that's what topic 4 is covering. And here we're talking classical mechanics. If we get to it at the end of the term, doubtful, I don't know for sure if we'll get there or not, we may do a little bit of quantum mechanics, which is modern physics, they call it. Things did change a little bit with that. But there you're talking submicroscopic stuff going on, things you never see in everyday type life. It's the stuff that's happening in electrons going down a fluorescent tube. Yeah, you do see it sort of there. You don't see that happening, you just see the results of it. So for now, we're going to stick with classical mechanics, the macroscopic view. This describes the relationship between the motion of objects in our everyday world, where we live, you know, what we can see and sense, and the forces acting on them. Okay? Conditions when classical mechanics do not apply, again, like I said, very tiny objects when you're down to less than atomic sizes, subatomic sizes. Or the other condition is when objects are moving near the speed of light. And of course, for an object to move near the speed of light, it's going to have to be very tiny, because a big object will never even get close to the speed of light. And we'll maybe talk about those kinds of things when we get to those last chapters, if we don't run out of term before we run out of chapters. So let's look at Newton's laws. These are the things that govern forces. This chapter will look at an introduction to Newton's 3 laws of motion, and we'll also do his law of gravity. Okay? There'll be some other stuff we do in the chapter 2, but they're all related. These laws are considered among the greatest achievements of the human mind, especially when you consider the mind that did it, you know, Isaac Newton. Not an excessively pleasant person, from all indication. Brilliant, though he didn't realize, I don't think he was brilliant. I don't think many others did either. He had a fairly rough upbringing. He was a premature baby, not expected to live. His father actually died before he was born. So he was raised by his mother until she remarried. And then the new dad didn't really want many old kids, so he wanted to start his own. So he got shipped off to a grandmother. And it was only after a while, his father had been a farmer, and his mother, when ultimately they took him back into the household, wanted him to take over the farm. And he wasn't a very good farmer, I'll put it that way. He was too busy thinking. And as it turned out, an uncle sensed his brilliance, I guess, though it wasn't very obvious. He said, this kid needs to go to school. So he went to Oxford, England, the great university there in Oxford. I believe it was Oxford, or Cambridge one. I always get those two crossed up. He was so poor, he basically washed clothes, cleaned rooms, and stuff like that for richer students so he could afford his tuition. He literally worked his way through college. Literally. I mean, not much, if any, support from home, and it was pretty humbling. The other students, usually from pretty rich families, looked down on him, and yet he passed them all. In fact, in about 3 years, he had passed everything that his professors could teach him. So as soon as he finished, they said, look, can you come and start teaching? In fact, the guy who was in the head chair of mathematics said, take it over. We want you here that much. You're beyond what I can do. And I don't remember where along that scope of time, but something happened. The bubonic plague, the Great Death, the Black Death, hit England. It had been racing its way through Europe, and it was just awful. I mean, sometimes killing a third of the population. It was just ravaging people, and no one knew what to do to stop it. Well, by the time it hit England, they had at least realized that it only went hit hardest in population areas. So rather than risk the next generation of minds at the university, they said, go home to the country. It doesn't seem to hit there, so Newton went home to the farm. Still wasn't a very good farmer, but at least now he had the tools in his belt to do some thinking. And in those 3 years the university was closed because of the bubonic plague, he developed these laws, which are among the greatest achievements of the human mind. The law of gravity never had been considered before. Many things in optics. He determined that light was actually a spectrum of colors, not just one color, white. Okay. And in order to do this, he had to invent a whole new branch of mathematics because the current math couldn't explain what he was discovering. So he developed calculus, an entirely new branch of mathematics, the three laws of motion, one of the greatest achievements of the human mind, law of gravity, and optics, many things in that, plus a few other things, just give or take, in 3 short years that he didn't have any teaching responsibilities. Pretty amazing character. Okay? So, this is exactly how he thought of it. This is how we have come around to thinking is the best way to approach this. Let's first talk about what forces are. I can remember my high school physical science class, 9th grade, that's what we took. I had the mean old football coach as a teacher for that, and I can remember old Pooley Hubert saying, a force is a push or a pull. And if you think Bear Bryant talked with a gruff voice, he didn't come close to Pooley Hubert. He was one scary old guy. Okay. So you can think of it, commonly imagined as a push or a pull on some object. Now, a little bit more elegant way of thinking of it, a force is a vector quantity. What does that mean? To be a vector quantity as opposed to a scalar quantity. Did I hear something? It has direction in addition to a magnitude. Okay? That's what we mean by a vector quantity. It has a direction in addition to a magnitude. Okay? Now, you could have a contact force. I push on the desk. I can't push on the desk unless I'm touching the desk. I can't go move desk, but sometimes I can't even push on it and get it to move. But that is a contact force. Or you could have a field force. I jump up in the air, not very far, and guess what? Gravity pulls me down. Nothing's touching me to pull me down. That's a field force. Okay? Contact forces result from physical contact between the two objects. Field forces act between disconnected objects. They don't have to be touching. In fact, they're better off not touching for a field force. So there are those two types of forces. Okay, so let's take a look at these. This is a spring force. I pull on a spring that's attached to the wall, and the spring's pulling back on me. Okay, but I'm in contact with the spring. I compress the spring. Now the spring pushes back on me, but I'm still in contact with it. Pull on the wagon, have to be in contact. I can't will it to move. I either have to pull or push. Kicking the football, okay? Seems like it maybe he does get that high before it leaves his foot. I don't know. It looks like it's pretty high up there, okay? But anyway, those are contact forces. Field forces, attraction between two masses, gravitational force, attraction or repulsion of two charges. That's a field force. They don't have to be touching. In fact, quite often they're not. Or the attraction of a magnetic material to a magnet, or sometimes the repulsion of two magnets with each other. Those are also field forces. Notice gravity is always an attractive force. Both electrical and magnetic forces can be either attractive or repulsive. Don't sweat those. Those are the next physics class. We're going to deal mostly with contact forces or gravitational forces. All right. Now, not only can you classify forces that way, there are certain other classifications, as in our fundamental forces. And these are all field forces here. The four major types of these, let's start at the bottom here, gravity. Okay? Any time you have two masses a certain distance apart, they will be somewhat attractive. Okay? The trouble is, gravity is a fairly weak force, so I can stand as close to this desk as I want to stand. I'm never going to be able to get it to move due to gravity, because gravity is a very weak force. However, it operates over long distances when it's strong enough. Okay? So you have to have an enormous amount of mass, as in the sun, the earth, the moon, those kind of orders of magnitude, before you start sensing gravitational forces. Now, I would have put electromagnetic forces next. Okay, so let's talk about them. That's what we're talking about with charges and with poles of a magnet. Okay? Those forces are stronger, believe it or not, than gravitational forces, but they typically don't act as long a range. Even though a magnet or a charge can overpower gravity on the short run, you'll never sense that between planets, electromagnetic forces. So they're stronger forces than gravity, but their range is much less. A weak nuclear force. Boy, these are pretty incredible titles, aren't they? Weak nuclear force, strong nuclear force. These are forces that are within the nucleus of an atom. The strong nuclear force, I think, is the one that keeps an atom from blowing up. Because if you think about it, what is the nucleus of an atom made of? Two fundamental particles. You want to know what they are? The nucleus of an atom. Protons and neutrons. What can you tell me about a proton? Positively charged, okay? And neutrons are neutrally charged. In other words, they're not charged. Now, nuclei of atoms are incredibly tiny, but incredibly massive, okay, for the size, you know. And here you have all these protons, sometimes as many as 100, in a really small space. Electromagnetic forces would have those repelling each other like crazy, okay? So the nuclear forces have to hold those in place. Again, much stronger than the other forces, but over a much shorter range, okay? So those are your four major fundamental forces. All of these are field forces. I started off saying that way. And they say listed in order of decreasing strength. Now, most of the time I've seen these two swap, but I'll take their word for it. The electromagnetic forces are stronger than weak nuclear forces. That means the strong nuclear forces are those that hold the protons in there. Because if it was up to magnetic forces, electromagnetic forces, they'd be blowing apart as fast as they could get. Speaking of which, Ryan is here. Okay. Has anyone else come in since I called roll? You haven't heard me call your name. Okay. Only gravity and electromagnetic forces we're going to deal with in mechanics. gravity in this course, electromagnetic forces in the next course, 202. You may do ever so small ones in here, but basically next course. Okay. As I mentioned, Isaac Newton, Sir Isaac Newton, and that's the time in which he lived. Can someone tell me about what was going on, say, here in our country at that time? This is the very earliest of the colonies. I can't remember if Georgia had been formed as a colony by this time. This is before the Revolutionary War, before anything. If anything was happening here, it was Columbia. Okay, and that was just very few settlements on the eastern seaboard. Of course, he was in England. It didn't much matter to him. Isaac Newton formulated basic concepts and laws of mechanics, universal gravitation, calculus, light and optics. It's almost like you name it, he was intimately involved in it. Carried the fields far farther than anyone else had even conceived before him. Incredible mind, an incredible mind. Like I said, not all that great a personality maybe, but an incredible, incredible mind. Actually, I mean, he lived to be, if you look at that, 85? Which is pretty old for those days, but some of his alchemy experiments, he was sort of also into chemistry too, he probably had, been exposed to mercury and some other things that may have actually damaged his health some. But boy, 85 in those days was pretty good. All right. So let's look at his three laws of motion. Now, in general, they're related. So don't think of them each as separate, even though we kind of separate them. But they form a coherent whole. Okay? Now, this is probably not how Newton expressed them. We'll hit that a little bit later. An object moves with a velocity that is constant in magnitude and direction unless it's acted on by a non-zero net force. So that's basically Newton's first law. An object that is in motion, you'll hear people phrase it this way sometimes, stays in motion in that same line of motion at that same speed unless it's acted on by an unbalanced force or a non-zero net force. Okay? Now this was in stark contrast to what had been believed for centuries before his time. Aristotle had been the latest of the great Greek philosophers, and he did a lot with science, and he did mostly observational stuff, and he said natural motion on the terrestrial side, on the earth, is always at rest. Actually, before Newton was a guy named Galileo. Galileo said this first law pretty much initially. Newton refined it some, but Galileo actually came up with it. And it said but anyway, it was in stark contrast to what people had believed for centuries and centuries after Aristotle. So the net force is defined as the vector sum. Now remember, forces are vectors, velocities are vectors, so you're having to talk about vector sum. So the net force is the vector sum of all the external forces exerted on the object. And that's what Aristotle hadn't done. He hadn't taken into account other forces, specifically resistive forces like friction, air resistance, those kind of things. So, those were some of the problems, shortcomings he had. So there's Newton's first law. Okay? Let's look a little bit about those external versus internal forces. Any force that results from the interaction between the object and its environment, that's an external force. An internal force are the forces that originate within the object itself. They cannot change the object's velocity. Has to be prompted by an external force. Okay? Now, this probably isn't the best illustration of this, because you may have some grounds to argue this isn't quite true. But again, I think you'll find this a little hard to believe. If you were firing a rifle, okay, you hold the rifle up to your shoulder and aim it at the target, pull the trigger. The hammer mechanism hits the bullet, and because the material inside the bullet, let's call it TNT or explosive, let's just call it explosive, in the bullet is fairly unstable. The act of hitting that in a compressed space, creating some friction, makes it explode. The bullet flies out of the rifle. Okay? Now, when the bullet flies out of the rifle kicks back at you. Those are external, well, the actual, you pull the trigger, that's a force. The hammer hits the bullet, that's a force. But that internal explosion, it creates a force. We see the force goes in two directions. The net force before and the net force after are exactly the same. There's no new net force involved with it. Okay. Probably not the best example because it's so hard to believe, but it really is. Those are internal forces. The external force would be you pulling the trigger. Okay. That is about the only one in there. Everything else is internal. It sounds bizarre, but it really is the case. We'll see examples of this later that are probably a little bit better. Okay? Now, Newton's first law is sometimes called the law of inertia. In fact, I think that's probably about what Galileo, I don't know if he termed it that, but I always associate inertia or the law of inertia with Galileo more than with Newton because he came up with it first. Galileo, it's sort of bizarre too. According to some calendars, Galileo died the same year that Newton was born. Now, some calendars have it 1 year apart, but it was basically within 12 months. So it's almost like they tag teamed. I mean, they never, of course, met, and Newton would have been a child then for quite a while, but it was pretty amazing. Galileo down in Italy, Newton up in Great Britain. So inertia. Inertia is the tendency of an object to continue its original motion. Now remember, original motion may be a couple of things. You've seen me a couple of times already today push on the desk. Oh, there I got it to move. Okay? The reason I had trouble getting it to move to begin with, the desk inertia, its motion, was at rest. Okay? It had no original motion. It was at rest. And it takes force to make it change that inertia, to change its movement. Okay? So, but inertia isn't just, in that sense, inertia is inert, when it's not moving. However, when it is moving, you still take force to change it. I don't know who the preeminent fastball pitcher is in baseball now. There's probably several of them. At one time, let's see, in one of the texts, there was a picture of Tim Lennican or something like that that used to play for the Giants, and I think he's now with the Angels. Way back in history, Bob Feller was the real heavy fastball pitcher. Nolan Ryan then was about the time I was around. Randy Johnson was a really strong fastball pitcher. If you ever was the catcher for those guys, you probably had to put liniment on your hand every night because you have to exert a lot of force to stop that ball because it's going at its inertia was going at a very great speed. The tendency to keep that inertia, you had to exert a force to make it stop or slow it down. So that's what inertia is, the tendency of an object to continue in its original motion, that's both in direction and in magnitude. Okay? That would be in the absence of a force. Now, if you had forces acting on it, that will change the motion. Now, here's a thought experiment. You don't actually have to do this, but just imagine hitting a golf ball. Now, if you didn't want to use a golf club, you could just hit it with your hand. That's fine, right? Okay? Say you had a golf ball sitting on the desk and you slap at it. Okay? Now, think of hitting a bowling ball with the same force. Which one's going to move the most? The golf ball, well, sure, because it has less inertia than the bowling ball. The bowling ball has a greater tendency not to move. Okay? Golf ball, a lot less. You didn't want to hurt your hand? Use a ping pong ball. It's even lighter. Okay. The golf ball will travel further. Both resist changes in their motion, but because the golf ball has less inertia than the bowling ball, it's going to respond more easily. Kind of makes sense? Now, mass is another quantity that is so closely related to inertia. In fact, inertia is kind of the illustration of the mass, okay, the manifestation of the mass. Mass is a measure of the resistance of an object to change its motion due to a force. Wait a minute, isn't that what they said about inertia? The tendency of an object to continue its original motion. The measure of resistance of an object to changes in its motion due to a force. It's almost saying the same thing. The larger the mass, the less it accelerates, just like that bowling ball, when you have the action of a given force. Now, inertia again is a tendency. Mass is actually a quantity. The SI units for mass are kilograms. SI, System International. This is the only one of our SI units that has a metric prefix. Most of the things, this is base unit, like meter, second, liter, all those others, you just use the base unit. But the base unit for this would be gram, but a gram is such a tiny, tiny, tiny amount of mass, they use the kilogram as the base unit, or the SI unit for kilogram, which is 1,000 grams. Now, mass, however, is a scalar quantity. No direction is associated or affiliated with the mass of an object. It's just how much of the object is there. Okay? Now, anyone happen to know, I may have asked this question before, I think I did, what the U.S. customary unit for mass is? Slug, exactly. Okay? How many times have you used that in the last week? Never. In the last year? Never. In your lifetime? Never. You don't go to the store where you might want to buy a few kilograms. I was going to say kilos, but that would get you off on the wrong imagination there. A few kilograms of baked beans or potatoes or fruit or something. You'll never go to the grocery store and get a response say, I'd like 7 slugs of beans, please. They'll think you're nuts, because no one uses slugs. What do we usually use in the grocery store when you're buying potatoes? Pounds. Is pounds equivalent to kilograms? Actually, pound is a force measurement, not a mass measurement. They're related, but they're not the same. And pound is a vector quantity, not a scale. Force is a vector quantity, not a scalar. So they're really pretty far apart, though they are. You kind of use them interchangeably. So that was Newton's first law, or at least an introduction to it. Let's go back to that definition. It sort of bugs me. The book has a better way of saying it. Okay? From the previous slide on inertia, although inertia is the tendency of an object to continue its motion in the absence of a force, okay, mass is a measure of the object's, no, it's saying the same thing, resistance in motion due to a force. So those are intimately close together, okay? They have a really incredible picture in your text on page 83. I don't know if any of you, a few people have your book. And I don't know why they ever designed things this way in the beginning, but they do. They did. And they still do. I don't know. It's a locomotive that was coming into a train station, but obviously was going so fast, its inertia was so great, it went out of the train station, right through the wall, and down onto the street below. Pretty incredible. But when you think about it, a locomotive in itself is pretty massive, but then if it has a huge number of cars coming behind it, fully loaded and stuff, if you don't start slowing soon enough, you're not going to be able to exert enough force to change that inertia in time. And obviously, they didn't that time. Try explaining that to your stockholders. Okay? Now, so Newton's first law, just a quick recap, a tendency of an object to maintain its state of motion unless it's acted on by an unbalanced force. The second law is kind of the opposite side of that. If an object is acted on by an unbalanced force, then it's got to change its motion, right? Because the first law says it won't change its motion unless it is acted on by an unbalanced force. The second law basically said if an object is acted on by an unbalanced force, it will change its motion. And if it's changing its motion, what is it doing? Accelerating. Velocity is not a change of motion. Velocity, if that's constant, motion isn't changing. If it's changing direction, yeah, it's changing because velocity is a vector quantity. But if a velocity changes direction, something had to make that happen. So therefore, there had to be a net force acting on it, and therefore there was an acceleration. Even though it didn't change speed, it still accelerated. Okay? So acceleration of an object is directly proportional to the net force acting on it. Because you got to have the net force or you won't have it, but it's inversely proportional to the mass. That's what we're talking about with the ping pong ball and the bowling ball. The small net force can send the ping pong ball fly. Small net force basically is going to do almost nothing to a bowling ball. So it's directly proportional to the net force, the acceleration is, and inversely proportional to the mass. The bigger the mass, the smaller the acceleration at the same force, but the bigger the force with the same mass, the greater the acceleration. And this is net force. Okay, now, right now they're representing net force by that symbol there. Anyone know what that symbol is? The Greek capital letter for sigma. Anyone know what it means? sum. The sum of all the forces. So remember, forces are what kind of quantity? Vector quantity. So this sum is a vector sum. Don't just add up how much things weigh or something like that. That's not what it's meaning. You add not just the magnitude, you add the directional aspect as well. So the net force, that's the sum of all the forces acting on an object, divided by its mass, is going to produce its acceleration. Acceleration is directly proportional to net force, inversely proportional to the mass. Or written the other way, and this is the way that most of the time people will remember it. The net force on an object is equal to its mass times acceleration. In other words, you just multiply the mass by both sides of the equation, mass times acceleration. And most of the time people don't put the sum of the forces. They just say net force, meaning the sum of the forces, vector sum of the forces, is equal to mass times acceleration. Now, that can also be applied to three-dimensionality. So not only does it apply to horizontal motion, to vertical motion, or to two-dimensional motion, it applies to three-dimensional motion. We haven't really done much in 3 dimensions, so we won't sweat that too much now. But that's Newton's second law. There is a little tip they have at the bottom of page 83. You probably have already passed that in the slides, but here I want to mention it. Forces cause changes in motion. You can't have a change in motion unless you have a force making that happen. Motion can occur even in the absence of forces, but forces cause the change of motion. For instance, an object, say a spacecraft, once you get out of the gravitational field of the Earth, and mostly out of that of the sun and other things too, if that object is moving at a certain speed, it's going to continue moving at that speed unless you do something to change it. Okay? So therefore the it requires a force to make a change of motion, is what that's getting at. They have another application figure here that so far I haven't seen anything in the text that supports it. Maybe, I don't know, I don't see it yet. It's, I hadn't seen them phrased this way, but it's your seatbelt technology, the mechanical arrangement for the automobile seatbelt. Again, it responds to a change of motion, especially a very abrupt one, and it will try to keep you from responding to it as well. Okay. Let's look at the units of force. The SI unit of force, and by the way, let's back up one slide. Okay. Using this definition, net force is equal to mass times acceleration. What's the SI unit for mass? Kilogram. Acceleration, meters per second squared. So a kilogram meter per second squared is a force, is the unit for a force. A compound unit, kilogram meter per second squared, that's your unit for a force, especially a net force. The unit for that, here we hit sort of a, I don't know, I consider it almost an anomaly in science. Now, when Newton wrote the treatise that these forces were presented in, the three laws of motion, was called Principia. Well, that's not a very common word. It basically means principles, but Seems like my head is really congested today, and so I'm having a little bit of trouble talking clearly anyway. When Newton, and what I was getting at, Principia is not an English word. It's a Latin word. At the time when Newton lived, remember 16 to 1700s, all of science was basically written up in Latin. Now, strange, but true, even at that time, Latin was pretty much a dead language. There was hardly anyone who spoke Latin as his native language. Latin, I guess, originated in Italy, and it was the language of the early Roman Empire. But sometime after that, especially after the Roman Empire fell, no one really spoke Latin anymore. At least conversationally, I'll put it that way. Now, there was one place where Latin was spoken quite a bit. In fact, that's where the language continued to be studied and dealt with, and that was the church, the Roman Catholic Church. In fact, I can remember in my early lifetime, all masses are still conducted in Latin. And people began to wonder, what's the point of this? If I can't understand the words you're saying, why do I sit there and have to listen to them? Well, that argument reached some ears, and they decided to let people worship in their vernacular, their native language, so they knew what they were talking about, knew what they were saying. So Latin did continue in two places, and these were interrelated in the church and in the university, or science, because most of the universities were related to the churches, so that was considered Latin. So anyway, when Newton was referring to this, he may have used the term force or something like that, but generally he didn't. And he didn't use things like this. Force is equal to mass times acceleration. What he talked about was a quantity of motion. Later we're going to talk about that very quantity of motion, but that quantity of motion we now know to be the momentum of an object. Again, we're going to hit this in a later chapter, or later in this chapter. And he talked about that, so when he was talking about when he was talking about change of motion, he was not talking about motion specifically. He said change of that quantity of motion, that momentum. Okay? Now, does anyone remember what acceleration was? Yes? Acceleration. Pretty simple concept. What is it? The units even. Done a couple of labs where you calculated what's the second? Meters per second squared would be the units for it. Meters measures distance. Seconds measure time. A meter per second would be a measure of a speed or velocity. And a change of velocity, okay, and remember this, go back to the beginning. A change of position over a time interval is a velocity. A change of velocity over a time interval is an acceleration. So this will be a meters per second squared. Okay? Change of velocity per change of time. Okay? What if you took the mass and put it with the velocity? that makes, this is beyond what we are now, that makes a momentum. That was Newton's quantity of motion. And then you take the quantity of motion, the mass times the velocity, take a time rate of change of that, and you get a force. That's what Newton referred to as creating change. A change of the quantity of motion had to come from some net external force, and that was his change here. Okay? Now we'll get to that later. The reason I started off on this, we think in terms of forces. I don't know when this happened, maybe early on, maybe later. They define this force as a mass times an acceleration. Well, that mass times the acceleration, kilogram meter per second squared, that's kind of a mouthful of units, right? They decided to name that a Newton. Named after Sir Isaac, therefore it's capitalized. See, kilogram or even just gram, not named after anybody. Meter, not named after anybody. Second, not named after anybody. Newton, named after someone, so use a capital letter. Okay? Now, the U.S. customary unit of force is the pound. Again, that's a weight, it's a force, it's not mass. Okay? So 1 Newton is about a quarter of a pound, between a fifth and a quarter of a pound. So a pound is a bigger unit of force than a Newton is. Kilograms, I'm sorry, I said that backwards. A Newton's a bigger unit than a pound because, no, back off, okay. Yeah. 1 Newton is between a fifth and a quarter of a pound, so that means a pound is a greater amount of force than a Newton is. Okay, it takes to get 1 pound, you would have to have between 4 and 5 Newtons. So, yeah. Now, if you think about the reason for that, consider the reason for that. Well, we don't know what a slug is anyway, but just keep that in mind. That's the conversion. Now, summary of units is on table 4.1, bottom of page 84 in your text. Okay? There's a little blurb on Isaac Newton. Now, remember this, folks. And by the way, here my biggest class, my largest class. And how many papers have I gotten in so far? Oh, 0, okay? So don't forget about your research papers. Believe it or not, we're getting fairly close to the midpoint of the term. We're not there yet, but we're getting close. It's only a 10-week term, so don't let time slip you by. Don't wait till the last minute to do your paper. It just won't be as good a job as you need it to be, okay? But here's a blurb on Isaac Newton, like the picture we saw there. This can't be your source. Your source has to be outside the text, okay? You can get ideas from your text, but don't do that. Okay. Now, there's another thing coming up. We'll get to that in just a minute, too. So, here they named the unit of force after Newton, where he really didn't talk that much in terms of forces. He talked in momentum. Why didn't they name the unit for momentum after Newton? That would have made a lot more sense. But he called it quantity of motion. Okay. I think the table. The SI unit for mass, kilogram, U.S. customary, slug, doesn't even have an abbreviation. No one uses it enough to make it. Acceleration, meters per second square for SI, feet per second square for, U.S. customary. And then the force unit is a Newton, which is a kilogram meter per second squared, and a pound is a slug foot per second squared. Which is the thing we don't know what, I don't have a clue of what a slug is. It's a fairly reasonably large unit because a pound is bigger than a newton, meter is larger than a foot, second squares are the same in both, so a slug would have to be I'd say on the order of 12 or so times bigger than what a kilogram would be, but I don't know that for sure because no one ever uses it. Okay. Let's look at some of these notes about forces before we move on. Forces cause changes in motion. Okay? A lot of time in physics, what we're really interested in are the changes, not the actuals. Okay? Remember, a displacement is what creates a velocity. Change of position over change of time, that's what is velocity. A change of speed over change of time is an acceleration. Later we'll see a change of momentum, the quantity of motion, is how he defined that change over time is forces. So he did talk about forces, but not in the same way we do. Generally, okay? Motion can occur in the absence of forces, but changes of motion don't occur unless you have a force. All forces acting on an object are added as vectors to find the net force on the object. Okay? The MA, mass times acceleration due to gravity, is not a force itself. That's the net force, the sum of all the forces. Let me give you sort of a dumb illustration of this. Okay? Let's say we have an airplane. You come up with how much you think that airplane weighs. Say again? Estimate. 2 tons? Good choice. Good estimation. This is Dakota, right? Yes. Okay. So here we have a 2-ton aircraft. Okay? It's flying along here in flat, level flight, constant speed. What are the net forces acting on that airplane? What's the net force acting on that airplane? Okay, we didn't give it a speed. Give me a speed for that airplane. Make up something. 140 miles per hour. Probably a propeller plane. Most jets are faster than that. So a 2-ton propeller plane flying at constant elevation, straight line motion, flying at 140, you said? Is that what you, okay, 140 miles per hour, okay? What's the net force acting on that plane? Does it have a net force acting? What do you think? Is there a net force acting on the plane? Okay, now gravity is for sure acting on the plane. It weighs 2 tons, didn't you say? Sure, gravity is pulling downward at 2 tons. Well, that's not a net force, that's a component force. That is a specific force acting on the plane. Okay? What's the net force acting on the plane? Say again? Okay, now I said, you're hitting really close to the thing. Notice I said it was a level flight, straight line motion at a constant 240 miles per hour. So it's not accelerating. So guess what? The net force is 0. Sure, the force is acting on the plane. Gravity for certain is pulling down on a 2-ton plane. Okay? But, in addition to gravity pulling down, it's traveling 140 miles an hour, lift is picking the plane up. Otherwise it wouldn't fly, would it? And sure, you got exhaust going out the back, which is pushing the plane forward, but it's also running into air resistance. It's retarding its motion. So if it's at a constant speed, it's not accelerating. So the net force would be, and the net force is ma, and if that plane's not accelerating, the net force is 0. Okay? So ma is not a force itself, that's the net force acting. Okay? Remember that Newton's second law is a vector equation. Now, does anyone know what's holding the plane up? I said lift was, but that's sort of a nebulous word. Okay, I'll ask you a couple of questions here. If I blow underneath this piece of paper, what is it going to do? Yeah, it comes up. What if I blow over the top of this piece of paper? What's it going to do? Go down? What did it do? Does anyone know why? There is a type of a force or a principle called Bernoulli's principle. And Bernoulli's principle says that the pressure on an object is inversely proportional to the speed of the object. Okay? Now, what that means is, go back. Oh, by the way, I meant to ask this. Kiara's not here yet, is she? She left something in here. Someone else left something in here. I think it was from this class. Yeah, because it's 201 test 3. This notebook belonged to any of you. It was left here after the last class. I didn't see one. Did you? I didn't put any pages here, so I don't know. She had little notes or whatever. Huh? Yeah. Okay. I only opened the front cover. I didn't look everywhere else. But if anyone hears of anyone missing a notebook or their last test, there it is. Also left in here, maybe from the other class too, a pen and a pencil. Maybe from my other physics class, but it was Monday. These were left in here. Well, no, the pencil was left in the lab. Well, things were left somewhere. So anyway, I meant to ask that earlier. All right. So these are notes about forces. I think that's hit most of them. Before we move to gravitational force, there is a quick quiz, 4.1, on page 84. Okay? Which of the following statements are true? Okay? Now, it could be one or more of them. I guess it could be none of them, but let's assume at least one is true, but it may be more than one. So here's number A. An object can move even when no forces act on it. True or false? Yes, it can. Okay? That plane flying, well, there's certainly some forces acting on it, but in outer space, where there's no gravity and anything else, it can keep moving, with no forces acting on it. So that's true. So A is true. B, if an object isn't moving, no external forces act on it. That's not true, you say. Okay? What would be a counterexample there? What's that? Okay? Am I moving? That means there's no external forces acting on me? Gravity is always acting on you. Very good, yeah. So that one's probably not true. Okay? It didn't say net external forces, it said external forces. So B would not be. A would be, B is not. If a single force acts on an object, the object accelerates. single force acts on an object, the object accelerates. That's not, yeah. I think if indeed you mean that's the only force acting on it, if it is acting on it, I think it's got to accelerate. So I believe C will probably be true. Okay? D, if an object accelerates, at least one force is acting on it. Yeah, I think that's got to be true. E, if an object isn't accelerating, no external forces is acting on it. That plane wasn't accelerating and lots of forces were acting on it. Oh, I never finished that, did I? Okay, sorry. Let's go back to the thing. Why did I do this in the first place? Bernoulli's principle said the speed of an object is inversely proportional to the pressure on it. Well, you've been on planes before, right? Or at least you've seen planes. When they go to take off, they go down that runway, gunning the engines, spewing out stuff, going faster and faster. And then when they reach a certain speed, they lift off. What's happening? Think about those wings. In fact, this is what Wilbur and Orville Wright did. They looked at the wings of birds. How do birds fly? And if you'll notice, the wings on a plane and a bird are bigger on the front and tail off on the back. Okay? Bigger on the front side and tail off on the back. They're also tilted downward like this. So when they're going down, there is a force pushing them up like this. But more than that, there's the air that they run into here has to go further over the top than it does over the bottom. So therefore it speeds up over the top, slows down on the bottom. That's what provides lift. The change of pressure, more pressure up than moves down. So that's what happens. The lift has to exceed the gravitational force. So even though that was a 2-ton plane that we had in our earlier example, has enough lift to exactly equal that to keep it from falling. Okay? So there are net forces acting on it. It could be Bernoulli's force. Okay, sorry. Got away from this. So if an object accelerates, if an object isn't accelerating, no net force is not. That plane, lots of external forces are acting on it, but it's not accelerating. F, if the net force on an object is in the positive x direction, the object only moves in the positive x direction. If the net force is only in the positive x direction, the object moves only in the positive x direction. All right? No. Okay, you're right in not thinking so. Okay? If you can imagine traveling down a highway at a high rate of speed. In fact, was it yesterday afternoon? I saw it on the way home. Obviously, this one car was traveling down the highway at a high rate of speed. Must have been too high for the tires to grip the road because it may have just rained or something. And anyway, that car had hit something, another car, a truck, a tree, or something. And its motion was this way, the force was that way. And crashed the car, crumpled the car, It wasn't a pretty sight, okay? So yes, if the net force acting on an object, that was the tree acting on the car, was, say, in the positive direction, the car was coming this way, the car still moved this way and wrapped around the tree. Okay, so that wouldn't be. So let's see, which of the following statements are true? We said A was true, B was not, C we thought was true, D was true. So I think that's all, A, C, and D, I think. Oops, that's not the right place. Okay, this was topic 4. A, C, and D are true. Very good. All right. Now, there's several examples here, or a couple of them anyway. Example 4.1 is an airboat. 4.2 is horses pulling a barge. All right. Does anyone need either of those to be done, or are you ready to move on? Want to see a problem done or not? Huh? I can't hear. Move on, okay. All right, so let's move to gravitational force. Now, this is a specific force, okay? I think Courtney was saying gravity's acts on everything, okay, if you're in the gravitational field. So gravitational force, mutual force of attraction between any two objects. Now, later we'll get to the mutual part of this. That's law 3, okay? Law of motion 3. But still, it's true here too. Between any two objects. It's expressed by Newton's law of universal gravitation. Funny, we're on the universal law of gravitation when we haven't hit the third law of motion, but that's okay. Expressed by this, every particle in the universe attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In fact, most of your non-contact forces, your field forces, follow an inverse square law. Okay? I'm not as familiar with strong nuclear forces, so I can't say for sure on that, or even weak nuclear forces, but I know that gravitational forces and electromagnetic forces do follow 1/r² squared. Okay. Now it said proportional to. How do we change a proportionality to an equation? Multiply by a constant proportionality. So the proportional symbol becomes equal some constant. In this case, the constant is the uniform universal gravitational constant. Okay, universal gravitational constant, and that's capital G. Now, we often refer to the acceleration due to gravity as little g. Okay, the universal gravitational constant is capital G. They are very different quantities, so don't even think of them as the same. When we use force due to gravity, quite often we'll say F sub G, which is just identifying this as a gravitational force, not talking about the acceleration due to gravity, which is also little g, nor with the universal gravitational constant, which is capital G. But, as we said earlier, this is not a very strong force. I don't feel any super attraction to the desk. I mean, I like the desk, but no super attraction to it or anything, because this number, this universal gravitational constant, is an incredibly small number. You have to get some very huge masses here, even though I'm pretty big, I'm not that big, masses here before you start actually sensing that force. Okay. However, they do go over large ranges of space. So, let's see if they give. No, they don't. So let me give you what this G is. I said it's a pretty small number. Here's what it is in SI units. 6, where is my pen? Not operating. Let's see if I can get my pen to operate. Well, there we go. All right. G is equal to 6.67, reasonable sounding number, until you see the exponent, times 10 to the negative 11, and the units are Newton meter squared per kilogram squared. That is a small number. that would be 0.00000000667. A very small number. Newton meter square per kilogram square. Now, do those units make sense? Well, yeah, forces are measured in Newton, so you have to have a Newton over here. This is kilogram, and meters squared. So you have to have the Newton somewhere, so it has to be in the unit. And there's no meters over here, so you have to have meters squared up top to cancel out the 2 meters down here. And then there's no kilograms over here, so you have to have per kilogram squared to cancel those out. So that's your universal gravitational constant. Now, very, very small number. That's why that's me. Probably on the order of less than 100 newtons. Yeah. Let's just, less than 100 newtons. Okay? The distance between us is less than a third of a meter. Okay? My mass is, like I said, less than 100 newtons, around 100 newtons. Let's call it 100 newtons. The desk, I'm guessing that's, let's call it 100 newtons. It probably isn't. So that would be 100 times 100 is 10,000. The distance between us is a pretty small number. Okay? Let's say a third of a meter. So this would be a ninth of a meter. Let's just round that to 0.1 meter. A tenth of a meter would be 0.1. So we're dividing 10,000 by a tenth. Okay? So that would be 100,000. 100,000 is 10 to the positive 5. When you multiply that by 10 to the minus 11, you still have a billionth of a newton. Okay? No, I'm not feeling that. I'm not feeling that. 0.0000001 newton at all. Okay. When you're talking about force due to gravity, quite often we call that weight. The magnitude of the gravitational force acting on an object of mass m near the Earth's surface is called the weight, or little w. Okay? Mass is little m, weight is little w. Okay? Later we'll get work, which is a capital W. That's why we have to stress that's a small w, lowercase w. Mass, sometimes in some problems you have a little object and a big object. Little object you'll put little m, big object capital M. But that's usually the only parameter we use for m. So here's the formula for weight. Weight is equal mass times the acceleration due to gravity. Because remember, weight is a force, so it's a vector quantity, has to have an acceleration associated with it. That acceleration is the acceleration due to gravity. And just like before, we said weight, a force was mass times acceleration. The mass of the object times the acceleration due to gravity, which is 9.8 meters per second squared, that's going to give you your weight. That's a special case of Newton's second law for a specific force, not a net force. Net force is mass times acceleration of the object. This is the acceleration due to gravity, a specific acceleration, and this is the force that is associated with that. So that's why when you go to the grocery store and you put your grapes on the scale, the outer thing may say pounds, but the inner scale says kilograms. They're not the same. This is a scalar quantity, and it's the SI unit. That's a unit of mass. This is a vector quantity. That's a unit in the U.S. customary system. That is a force. So how can you compare the two? Well, the acceleration due to gravity is a constant anywhere near the surface of the Earth. if you're in the bottom of the Dead Sea Valley, on the top of Mount Everest, acceleration due to gravity is just about the same. Even if you're up there in an airplane, as long as you're not way, way up there, acceleration due to gravity is about the same. It's the acceleration due to gravity constant anywhere on or even near the surface of the Earth. Now, if you get outside our atmosphere, it starts dropping off. Not because of our atmosphere, you're just getting too far away. G can also be found from the law of universal gravitation. And we will show that now. Nope, we're not going to show it now. Okay, let's do it. Okay. What we said before is that force, this is force due to gravity, is equal to G m over r squared. Now we are on or near the surface of the Earth, right? So this is our mass. This is the mass of the Earth. So the force due to gravity would be our mass times the acceleration due to gravity. That must be these other units here. So let's see what we get if we multiply those together. Does anyone have a calculator today? Okay. G is 6.67 times 10 to the minus 11 kilogram. I'm going to give it the way they did in the book, which is Newton meter squared per kilogram squared. Okay? Take that number, multiply it by the mass of the Earth. Well, anyone know that off the top? I don't. There's the conversion factors, the different courses I teach from. Here we go. Back inside cover, physical constant, mass of the Earth, often called capital M sub E, 5.98 times 10 to the 24th kilogram. 5.98 times 10 to the 24th kilograms. Okay, that's kg, is ugly to read. Over r squared. Well, how far are we from the center of the Earth? That would be the radius of the Earth. If we're on the surface, we're the radius away. Radius of the Earth at the equator, we're going to assume it's about the same here. That's 6.38 times 10 to the 6 meters. 6.38 times 10 to the 6th meters. But we got to square that. Okay? So if you got your calculator, now does everybody know how to use scientific notation on your calculator? What key to hit for that? It's usually an EXP key, an EE key. There's some key that usually you just hit that and you go to scientific notation. Alright? So I'm going to give it to you as you hook it in. 6.67 EE or EXP. Don't do times 10 to the minus 11. Do that EE or EXP key, and then you'll see two little digits come up. And most calculators you'll do now the not the subtraction key. This minus key is the one in parentheses, that parentheses minus, not the one that says just the long minus key. That means subtraction. This is your negation key. FA, right? Okay. Has anyone else come in since I called roll? If you have people leave since I called roll, there's no one else. Okay, 6.67 EE or EXP, the negation key in parentheses, 1 times 5.98 EE or EXP, 24, divided by, that's the division key, 6.38 EE or EXP 6. But then once you have that entered, then find the x squared key, square that number, and then hit equals. Anyone got it? 62.5 is not quite right. Let me watch you do that. Okay. Wait. Go up to the comments. Wait. No. There it is. There's your new EE. Okay, second EE. Okay, then do your negation, 11. Okay, times. Okay, 5.898 EE. Second. Okay, 24 divided by. Okay, and do the 6.38 EE. 6. Square that. Oh yeah, you can close that if you want to. And square that. There's your square root. Okay, that's fine. Equal. Look at that. Rounds to 9.8. That's the acceleration due to gravity. Everybody get it? Is anyone not able to get that? Okay. Acceleration due to gravity taken from the universal gravitational equation. All right. Any questions? Okay. Now, did anyone else come in while I was talking? There was movement, but it may have been someone leaving. Okay. More about weight, as if I wanted to know more about weight. Okay. Not sure. Yeah. Okay. Weight is not an inherent property of an object. Mass is. Can anyone give me an illustration of why that's a true comparison? Weight is not an inherent property of an object. Mass is. Okay, now this is never going to happen, but if it were to happen, that I went into outer space, okay? What would be my weight there? Not quite zero, but close to it. My weight would be greatly reduced. We say they're weightless when they're just sort of floating around up there. As long as they're in a gravitational field, they got a little bit of weight, but not much. They got far enough away from the Earth, they're not close enough to the sun or the moon, they're almost weightless. Okay? So, what is my mass? My mass is the same as what's here on Earth. So weight is dependent on being in the gravitational field. If I was on the moon, I'd weigh a sixth of what I do now. Okay? And Allison. By the way, I asked this question earlier. I'm going to ask it again. Now, Tierra is not here. Do these objects belong to anyone here? It may have been my second class that someone left a notebook, a pen, and a pencil, and at least one of these was left in the lab. It may belong to the lab, I don't know, but I didn't want to leave any stuff there that didn't. But I know this is someone in this class because they have a Physics 201 test here that I gave out last time. Huh? Oh, this is Tierra's too? Okay, we can both do. How about the pen or pencil? Okay. Will you see her? Okay. This is her. I know this is her, but check the writing in there and see if that looks like hers too. What's that? Oh, okay, good. glad we located it. Okay. All right. So weight is not an inherent property, mass is. Weight depends on where you are. Not where you are on the surface of the earth, or more like what planet are you on. I wonder that sometimes. No, but if you're on the moon, your weight is about a sixth of what it is on the earth. If you were on Jupiter, it would be a huge amount more. So if you want to get on a really good, effective weight loss program, go into outer space, okay? You're bound to lose weight. You won't lose any mass, but you're bound to lose weight. Okay, never mind. We aren't interested in that, are we? All right, now we jump to Newton's third law. Oh, wait. Before we get to his third law, there are two quick quizzes. 4.2. Which has the greater value, a Newton of gold on Earth or a Newton of gold on the moon? Newton is a measure of force, okay, which depends on gravitational field. And which gravitational field is stronger, that of the Earth or the moon? The Earth, by a lot. So if you had a Newton of gold on the moon, you got a lot of gold, okay? Because the same weight of gold on Earth would be about a sixth of that. So you'd have 6 times the mass of gold on the moon to get 1 Newton than what it would be on Earth. I'm not sure it would pay for the trip, but it would be nice to have, okay? Oh, I'm sorry. Yeah, it was multiple choice. The first answer, Newton of gold on the Earth. B was a Newton of gold on the moon. Or C, the value was the same regardless. B. Okay, let's make sure they got it right in the back. Topic 4 to B, or not to B. Okay. 4.3. Respond to each statement, true or false. Okay, sort of like we did on the last one, only, okay. True or false? A, no force of gravity acts on the astronaut in an orbiting space station. No force of gravity acts on an astronaut in an orbiting space station. True or false? Make a guess. You have a 50-50 chance. Say again? In an orbiting space station. Okay? You say it's true that no force of gravity acts on the astronaut in the orbiting space station. Is that what you said? Okay. Not quite. Here's the key word here, believe it or not, is orbiting. If it's orbiting the Earth, that means the Earth is keeping it pulled in. You may not sense it, but it is there. So that one, I think, is a false. We'll see at the end. Okay, so we got a false for A. B, at 3 Earth radii from the center of the Earth, the acceleration due to gravity is 1/9 of its surface value. 3 Earth radii from the center of the Earth. So here's the Earth radius. So we're on the surface. Now we go 1, 2 more from the center of the Earth. That the acceleration due to gravity is 1/9 its surface value. Yeah, that would be true. Okay, so what we have, false, true. C, if 2 identical planets, each with surface gravity G and volume V, coalesce into one planet of volume 2V, the surface gravity of the new planet would be 2G. Oh, that's sort of a tricky one, isn't it? If 2 identical planets, each with surface gravity G and volume V, coalesce into one planet with volume 2V, or not 2V, okay? The surface gravity of the new planet would be 2G. Okay? Here's the key to that one. The masses would definitely add. But the volumes, we added the volumes, so V plus V is 2V, but volume is 4/3 pi r cubed. Okay? So, now the new volume would be 8/3 pi r cubed, right? You just doubled the volume, right? Now, what happened to the radius? Okay? The original radius was r. So, V is equal to 4/3 pi r cubed. This will be original radius. And 2V is equal to 4/3 pi new radius cubed. Okay? No. 8/3. You doubled the volume. No. No, okay. Sorry about that. You doubled the volume, which was the original, but this is the same as 4/3 pi r new cubed. Okay? So what happened there? 2 r original cubed is equal to 1 r new cubed. Okay? So the new radius is equal to the cube root of 1 over the cube root of, let me rewrite that. Yeah, my eraser's not working. Okay. 1 over the cube root of 2 times r, I said that backwards. It's just the cube root of 2. R O cubed. Okay? That's rather strange, but it's true, I think. So the new radius, oh, I'm sorry. I took the cube root of that. The new radius is the cube root of 2 times the old radius. Okay? Now, yeah, this is such a complicated problem. So, the acceleration due to gravity relates to the mass, which is doubled, 2m, divided by the radius squared, which would be 2 to the 2/3 r old squared. Okay? And this was the ratio before. Here's the ratio now. So if someone will do 2 divided by the this number, okay, this number is greater than that. That's the point, okay? So no, it will be by a ratio of this times G, not 2 times G. So the answer is no, it's false, but it's really pretty complicated to get there. So the C would be false, I think. D, 1 kilogram of gold would have greater value on Earth than, wait a minute. Okay. Did I get off base here somewhere? Respond to each statement, true or false. Oh, no. Okay, I'm sorry. C was only dealing with the 2 planets, so that was false. D, okay, it has nothing to do with the 2 planets. 1 kilogram of gold would have greater value on Earth than on the moon. True or false? Say again? I can't hear. Oh, a question. 1 kilogram of gold would have greater value on Earth than on the moon. A kilogram of gold is a kilogram of gold is a kilogram. Pound of gold is not the same because that depends on your gravitational field, but a kilogram of gold is the same mass of gold as it is anywhere else. So that should be false, okay? Except there's really no place to spend it on the moon. No, that's not what they're talking about. Okay. So I'm lost track of what they were now. False, true, false, false. I believe that's what we said. Okay. Very good. All right. Let me erase. Hit the wrong key, sorry. All right. Newton's third law. If an object 1 and object 2 interact with each other, the force exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force exerted by object 2 on object 1. That's Newton's third law. It's called action-reaction. And I understand, this is what I've read or something, that Newton said it this way. If I push on a rock, the rock pushes on me with an equal but opposite force. So I'm going to try that right now. I'm going to push on the desk with my finger. Okay, I am pushing. I really am. Now take a look. Yeah, the desk is pushing on my finger too, with an equal but opposite force. That's Newton's third law. Action-reaction. Now the first 2 laws, we're talking about one object and the forces on that object. The third law is talking about 2 objects and the third law forces on them. Okay? Those are always equal and opposite. Okay? This is equivalent to saying a single isolated force cannot exist. Because if the force exists one way, there's an equal and opposite force the other way. Now, a single isolated force could exist on an object, okay, but then that object is pushing back on whatever is pushing on that. But on that object, there could be only one single isolated force. Okay. F sub 1, 2 may be called the action force. That's the force of object 1 on object 2. That's this force. Object 1 is pulling on object 2 with a force in this direction. And F21 is the reaction force. The force of 2 is pulling on object 1. Now it doesn't matter what their masses or anything else in, these forces are always, always, always equal and opposite. Okay? Now, if object 2 was much more massive than object 1, then the acceleration of object 1 would be far greater than it would be of the acceleration of object 2, because the forces are equal. If this mass is much greater, its acceleration is less. If this mass is much less, its acceleration more, because the forces are equal. Opposite in direction, but equal in magnitude. Okay? Now, actually, either force can be the action or reaction force. It doesn't have to be bigger and smaller or whatever. The action and reaction forces act on different objects. That's what's different about the third law, is that the action and reaction forces are always on different objects. Whereas your first and second laws, you're always talking about the net force on an object. One object, not the reactive forces. Okay. So here are some action and reaction pairs. Okay? And are y'all familiar with a vector called M? It's usually called the normal force. Now, what does normal mean? Average, every day? No, that's not what it means in physics and mathematics. What normal means is perpendicular. Okay? Here I'm pushing at an angle, not perpendicular. Here I'm pushing perpendicular to the tabletop. This would be in alignment with the tabletop. That's perpendicular. So perpendicular is a right angle. Okay. So N is called the normal force. That's the force that the table exerts on the TV. Okay? I'm going to give you a little bit of an example of that. Let's just imagine that we had, what length would that be? Let's say we had a 12-foot 1x6 plane. I'm going to go from here to there. Okay, y'all know what I'm talking about. 1x6. You could even make it 1x8 if you wanted to. Okay? Now I'm going to step off of here. Let's make it a 15-foot, so we have a little bit here, a little bit there. So I step on the plane. What do you reckon? If I go to walk across the plane from this desk to there, what do you reckon is going to happen? Second, I'm going to fall, he says. Okay, thank you very much. I don't have any balance. That's what you're saying? Now, if I can say, make it a 1x10, or 1x12, something big enough that I'm not going to fall, okay? But it's only 1 inch thick this way. 15 feet long that way. Do you think I can walk from here to there? What do you think is going to happen? Y'all either be very kind to me. Huh? Why not? Yeah, 1 inch thick. What's going to happen? Yeah. Okay, what's going to happen? Tell me. Why? Huh? Okay, what's going to happen? The board's going to go down. Now, either it's going to break, likely possibility, because I weigh too much, or, okay, just made it in for lap time, okay? That's okay, we're glad you're here. It's Bria and Raven, right? Thank you. While I'm doing this, let me go and mark everybody else. If A is still here, Nick hasn't made it in yet. Tiara hasn't made it in yet. Courtney is still here. Raven is too. Shakina is still here. Charity hasn't made it in since the second day of class, so I doubt if she's coming back. Courtney Humes is still here. Ambry hasn't made it in. She wasn't here. Well, she was here at the beginning of class, but not at the end before. Essence is still here. Ryan's still here. Darius is still doubting if I can. No, I'm sorry. It's still here. Monique is still here. I see you. Sasha is still here. Allison, yes, is still here. Darius doesn't think I'll make it. Okay, but he's still here. Scarlett hasn't come in today, has she? Okay. Will's still here. Brianna's still here. Naya is still, no, Naya had, I guess she had to leave. She left anyway. Dakota's still here. Alright, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 2, 4, 6, 8, 10, 12, 14, 16. Got it. Good deal. Alright, so what we have, I was illustrating what a normal force was. The board is trying to push up, but it can't push up with the same force that I go down. So the board is either going to sag till it hits the floor, break, or something, but it's not going to, I don't think I'll be able to walk the plank that far, even though I was in the Navy. No. Okay. So that's what a normal force is. Now this table, on the other hand, let's say this book right here weighs about 1 to 2 kilograms, something like that. It hits on the tabletop and it doesn't move. It doesn't sag or anything. That means the tabletop's pushing up with the same force the book is pushing down. That's Newton's third law of force. Okay? So N is the force of the tabletop pushing up on the computer. The computer, the force due to gravity, is pushing down here, and that's exactly, these are Newton's third law of forces. Because this force is on the computer, this force is on the this is the force due to gravity on the computer. This is the force due to the tabletop on the computer. And guess what? Since it's not sagging or breaking, those two forces are equal to objects, so it's not moving. Those are second law forces, maybe even first law forces, no, yeah, it could be, but not third law forces. The third law of force is the computer pushing, the tabletop pushing up on the computer, that's the normal force, and the computer pushing down on the table, that's its normal force down on the table. Now, sure enough, this is the same magnitude of that for certain, but the thing is, this is computer on table, this is earth on computer. So you see, earth on computer, table on computer, they're both on the computer. They're not third law forces. Computer on table, table on computer, those are on different objects, each on the other. That is a third law force. Now the one that's missing there is the computer is pulling up on the earth at the same force the earth is pulling down on the computer. Are you kidding me? I'm pulling up on the earth at the same force that's pulling down on me? It's true. When I jump, I push down on the earth because I happen to have spring. I don't jump very well, but I push down on the earth. I'm pushing on it, it's pushing on me, and when I land back on the earth, I push on it, it pushes on me. Does the earth move just because I jump? No, because think of the difference in my mass and the earth's mass. Okay, I may be massive, but I'm nowhere close to that. Okay? So Newton's third law of forces are always there. The same force with which the earth pulls down on the computer is the same with which the computer pulls up on the earth. This makes no difference to the earth at all, but that does make a difference to the computer. Because the earth is hugely massive, the computer is not. So N is always perpendicular to the surface. That's what it means by normal. N is the reaction force of the TV on the table of the action force of the table on the TV. Okay? So prime are equal but opposite. Just like FG and FG prime are equal and opposite, because they're pulling on different objects, even though they all have the same magnitudes. Okay. Another action-reaction pair. Oh, I just did this. F, the force of gravity on the computer is Fg. As the force of the Earth exerts on the object, and F prime of G is the force the object exerts on the Earth. They are equal and opposite, even though the Earth doesn't even notice, the computer does, because the Earth is so massive, you don't see any acceleration or anything else with it. Okay. Now, forces acting on an object, those are not action-reaction force, not third law force, because both actions are on the same object. Table's pushing up on the computer, gravity's pulling down on the computer. They're equal and opposite. That means the computer's not accelerating, but those are not third law forces. Okay. N prime and F prime, F to G prime, they are equal and opposite, but they're acting not on each other. N prime was the computer on the table, and F to G prime was the Earth on the computer. So even though they're equal and opposite, they're not third law forces, because they're not the same, the objects acting on each other. Okay. Now, before we get into the applications here, let me give you just another couple of kind of dumb examples of action-reaction forces. If I said an aluminum bass boat, do any of you have anything that comes to mind? I have no clue of what I mean by that. Answer me. Yes or no? No, no clue at all. Anybody have a clue? A John boat. Could be a John boat. Okay? Very lightweight boat. Aluminum. That's why I said aluminum. And usually just one or two people is all that's going to be in it, right? I guess you could have bigger ones. That's about normal. Very lightweight boat. Okay, can you imagine pulling up to the dock, and your friend you thought had tied the boat up, but he was fiddling around and didn't do it, or I don't know what he did, and you go to step off of it. What happens? The boat moves that way because you're exerting a certain force on the boat. The boat being very lightweight is not exerting much force on you. The boat moves away and you actually step into the water. And you're not very happy with your friend. Okay? Now, I was on the USS Forrestal, which is an aircraft carrier that was something about like 22 stories high, not from the keel to the bridge. Okay, it could carry close to 100 aircraft, all the fuel and for the ship and the aircraft, and about 5,000 people when we had the air wings aboard. So it's a pretty massive hunk of steel. Flight deck was probably 6 to 8 inches thick, solid steel. Okay, really massive. We pulled into port, and I wouldn't have done this, but if I had stepped off the ship to go ashore, would I fall in the water? No, because even though my force is equal to the force of the boat on me, my force on the John boat is equal to his force on me, because it is so much lighter, its acceleration is far greater, the aircraft carrier hardly accelerates off. I accelerate off of it, but it doesn't accelerate. Those are equal and opposite forces, but I don't move the ship, but I can move the John boat big time. We'll see some other examples later. So let's look at some applications of Newton's laws, or how we deal with applications of this. Here are the assumptions that we will make. We'll always treat the objects as if they're not objects, but particles. Just a little dot on the page. Now, for right now, we'll ignore rotational motion. Now, one of the labs we may do, I don't know if we're going to do this one or not. I do it in my physical science class, so I don't know if we'll do it in here. You have to sort of account a little bit for rotational motion. For now, we're going to assume no rotational motion or that it's negligible. Okay? Another thing, we're going to assume that the masses of the strings or the ropes are negligible. Okay? So if things are holding things together, we're going to say compared to these masses, these strings or ropes are negligible mass. Okay? We're interested only in the forces acting on the object. We will neglect reaction forces because those are on different objects. So when we're doing these applications of Newton's law, we're going to focus on the one object that we think is going to be moving, accelerating. Okay? Now, now, I didn't think about this earlier. Because we aren't having a lab today, we don't really have a break in between. Does anyone need a break? You'd like to have a break? Okay, you tell me. You want to keep it to 5 minutes, 10 minutes, 2 minutes, what? Say again? 10 minutes, you want the full 10. Okay, that means we'll go right till 3:30 then. Okay? Huh? Say again? I can't hear. No, I mean 5:30, I'm sorry. Whatever I said. Okay. That means we'll go right to 5:30. Huh? You don't want to take a break. Well, if anyone needs one, I want to let you have one. You say not? Keep tracking? Okay. Okay, if we don't take a break, we will get out, earlier. If you need a little break, we can still get out earlier, but not as much. So what do you want to do? Are you leaving for good or just taking a break? Oh, okay. Does anyone who's going to be staying need a break? Okay, we'll keep trucking then. But remind me then at 5:20 that we'll stop. Okay. More assumptions on the ropes, or strings, or whatever is holding the things together. We're going to assume that when there is a pull on this end, there is an equal and opposite pull this way. Now that's not, it is sort of a third law situation, but these are internal forces, not creating much of a thing in motion. And the reason for this is three maybe. First, we're ignoring any frictional effects on the rope. Even though the rope you might even hear it pop or something like that, a little bit, not break, we're ignoring those frictional forces within the rope. We're ignoring the mass of the rope. We already said that before. Okay? Now, the magnitude of the force exerted along the rope is called the tension. And here's what we're getting at. The tension is the same at all points in the rope. Here's what that means. When you pull on the rope, it doesn't stretch any. If it's stretched, that means you have different forces on it. So what we mean on a rope, massless, non-compressible, non-stretchable, and frictionless. We're going to assume all these things about the ropes. Make sense? Can you live with those? Okay. By the way, there were some other examples here. A hammer and a nail. This is Newton's third law of force. You hit the hammer on the nail pushes against the hammer, too. The nail pushes into the wood, but the wood pushes away from that. don't get your thumb in between, or else it becomes part of the action-reaction forces. There was another quick quiz, and let's hit that before we go to this, what we're talking about now. A small sports car collides head-on with a massive truck. Not a good picture, huh? The greater impact force in magnitude acts on A, the car, B, the truck, C, neither. The force is the same on both. A, B, or C. Small sports car, it's a massive truck head-on. The force, the greater impact of the force, that means the magnitude only, acts on the car, acts on the truck, or neither the same force on both. Got a 1 in 3 chance on that one. Make a guess. Okay. It certainly would seem that way, but Newton's third law says it's not that way. This is action-reaction forces, the same force on one as the other. The car is going to crinkle a lot worse than the truck because the truck is a lot more massive. The car may actually bounce off, but the truck's more massive, but the force is the same. The accelerations would not be, but the forces are the same. Okay, there's a B part, there's a second part to that. If I can find it, there it is. Which vehicle undergoes the greatest magnitude of acceleration? D, the car, E, the truck, or F, the accelerations are the same. I think I just said it, didn't I? Say again? Okay, my hearing's bad. Okay, the forces are the same on both. How about the accelerations? The what? Accelerations what? And which is greater? Car, truck, or what? Okay. This is not the right slide to put it on, but I'm going to. So we said the force on the car is equal but opposite of the force on the truck. Magnitudes are exactly the same. Force on the car is the mass of the car times acceleration of the car. The force on the truck is the mass of the truck times the acceleration of the truck. We know already the mass of the truck is way bigger than the mass on the car. So what does that say? If these things are equal, car acceleration has to be a great deal more than the acceleration of the truck. So what we have there was C, D. And let's see what they have in the back. CD. Good for them. That's compact disc. Okay. Now. All right. I'm looking for and not finding the stuff on the ropes. Okay, I'm not seeing it. So evidently these slides here, they're in 14.5 on the text. That's not the same in, in the slides, they're not the same in the book. But all these things are still true, okay? So we next move to free body diagram. And again, we're breaking from, here's one example, the new book is doing something different. So let me find the free body diagram here. Okay, there was the tensional forces, so I think that's where the rope stuff was. I didn't catch it before. Okay. Okay, here we are, sorry. Got a problem here. 4.3 in your text is normal and kinetic friction forces. 4.4 in the text is static friction forces. 4.6 in the text is what their applications of Newton forces. So hold on just a minute. I'm going to come back to this slide. There's the difference. So let's remind me to come back later. Let's do 4.3. I want to do it in the order that your book is. The force is due to friction. Okay? All right. When an object is in motion on a surface or through a viscous medium, there's always going to be some resistance to the motion. Okay? I push the chair along the floor. Now the floor is slick, but not too slick. The chair has 5 rollers, but they're not completely free. Guess what happened? The chair stopped. Now, according to Newton's first law, if there were no unbalanced forces, the velocity should not have changed, should it? I exerted a force on the chair, sent it going. There must have been unbalanced forces to make it stop. Now, what would have been some of those unbalanced forces? Well, there is a little bit of air resistance because this is sort of big here. See if it goes in front of you. Not a lot different, but maybe a little bit. Most of the difference is coming from the friction. Okay? You could hear it when it was rolling, couldn't you? That means there was friction. Okay? So therefore, there were frictional forces resisting the motion. Some air resistance, like when I did it that way, and also frictional forces, and also that way. So, there was friction. Anytime an object is in motion on a surface or through a viscous medium. Wait a minute. Is the room a viscous medium? The air in the room? Yes, very low viscosity, but it does have viscosity. Now, if I were pushing that chair through a pool of molasses, yeah, it's not going to go nearly as fast because that's a much more viscous medium. Okay? So, there will be resistance to the motion. This is due to the interaction between the object and its environment. That resistance is called friction. Friction. Friction of the air, friction the wheels to the floor. Actually, probably the greater friction is there's some friction because I turn this and you see it does slow down and stop. There's friction on the axis of the rotation. So there's friction all over the place. And all those are contributing to the stopping of or slowing and stopping of the chair. Friction is proportional to the normal force. Okay? Now, what was normal force? Perpendicular force. And would you mind helping? Okay, would you sit in the chair? Yes. If you could pick your feet up so they're not on the floor. Okay? I pushed it just as hard. Didn't go very far. You can go back now. Why? Because there's more weight on the chair on the floor. That's one thing, but more importantly, the floor was pushing up harder on the chair. That was the normal force. Not his weight on the chair, but the force that the floor was having to push up on the chair. Because guess what? His weight on the floor was not part of the motion because it's the chair moving, not the floor. So you had to have the normal force on the chair. So the force, okay, friction is proportional to the normal force. The greater the normal force up, the greater the friction. Okay? the force due to static friction, and now the text deals with normal forces, which we just talked about, and kinetic friction before it does before it does static. This is going to hit static and kinetic almost at the same time, with actually static being a little ahead. So let's remind me to come back here too. Well, yeah. Let's see if I can find. Yeah, here's. I want kinetic first. Okay, here's kinetic. Okay. Now this probably isn't going to be in as great a detail as it does in the book, so please read the book. Okay. Kinetic friction, and by the way, friction is usually given the symbol little f. It's a force due to friction, and that's usually the little f. Your net force is capital F sub n. Gravitational force is capital F sub g. Just about any force is going to be a capital F, except frictional force, that's going to be little f. Little f. And when they put sub k, that means kinetic. What does kinetic mean? Moving. Static means stationary. Okay? So the force of kinetic friction acts when the object's in motion. Okay? I push on the desk, it doesn't move. Why doesn't it move? Even though I was exerting a force, there's frictional force pushing back on me. That's why it doesn't move. I push on the chair, it does move. It's facing kinetic friction, not static friction. Okay? So the force of kinetic friction acts when the object's in motion. And here's the formula. Remember we said it's proportional to the normal force. That's the surface pushing up perpendicularly on the chair. So F sub k is equal to mu sub k times the normal force. Mu sub k is called the coefficient of kinetic friction. The normal force is the force of the floor up on the chair, which is exactly the same as the force of the chair on the floor, meaning gravitational force. But that's the normal force in this case. Variations of the coefficient of with speed will be ignored. Okay. Now, I think you can almost imagine if you're moving fast enough. Here's kind of an example of this. Have you seen those speedboats flying across the surface of the water? Once they're moving really, really fast, there's very little of the boat and water in touch with each other because they're moving fast enough they tend to hydroplane a little bit. So actually, their coefficient of friction probably would decrease with speed because if you're sitting down at very slow, it's hard to get that. We're going to ignore those kind of effects. Okay? So here we have, you're applying a force to the can, the trash can. Okay? The weight of the trash can is downward. Okay? Weight is always toward the center of the earth. The weight is mg. Force due to gravity, mg. Mass times acceleration due to gravity. We're assuming this trash can is on the earth. Okay? There's a normal force of the surface, whatever it is, concrete slab, the floor, whatever, that's going to be pushing up. It could just be the ground. That's pushing up. You're applying a force this way. There is a kinetic force, frictional force, always opposes the motion. Okay? The motion's that way because these two are equal and opposite, they don't contribute anything. But because this is greater than that, you will have acceleration, motion in that direction. Okay. When the magnitude of the applied force exceeds the maximum static friction force, which we haven't talked about yet, we're going to come back to that, the trash can breaks free and accelerates to the right. Okay? Now we'll come back to a graph like this a little bit later. But this is the frictional force, usually constant. We're not going to say it's varying any with speed. Usually it's constant, and it's mu, the coefficient of kinetic friction between the metal can and the concrete slab, whatever it is. That's some coefficient of kinetic friction times the normal force. If this can was full of trash, then it would have a greater weight, so it would have a greater normal force, so this would actually be longer. If the can was empty, then the weight is less, the normal force is less, and kinetic friction would be less. So it would take as much force to move. Does that make sense? Okay. Now, this is going back to static friction, so we'll come back to this slide later. Here is a table of some of your coefficients of friction. And right now we're going to focus on coefficients of kinetic friction. We'll come back and make a comparison with static. Steel on steel, typically not too great. Aluminum on steel, actually a little bit less. Not exactly like, but less. Copper on steel, that's even less. Rubber on concrete, that's a great deal more. Okay? Is that good, bad, or indifferent? Where would that be important for you? Say again? Driving your car on the road, the tires on the road. You want that to be a pretty large coefficient of static friction. Why? Won't that reduce your gas mileage? It would if you're going sideways. But guess what? If you don't have a high coefficient of friction, the tires are going to spin. That's why on a wet road, where that coefficient will now decrease, you'll spin your tires much faster than you would on much more quickly than you would on a dry road. If it's an icy road, you're hardly going to get any friction at all. Okay? So yeah, you want that to be a pretty high number. Okay? Wood on wood, not too bad. Okay? Pretty good. Glass on glass, I would have guessed that would be less than wood on wood, but they say not. Now, waxed wood on snow, on wet snow. Look how low that is. Is that good, bad, or indifferent? When do you wax wood and put it on wet snow? You may never do it, but when would someone? Say again? Snowboarding or skiing. Yeah, they wax those things, so they want to go just as fast as they possibly can. I would probably want to put grit on mine if I did it, which would slow down some, okay? But yeah, that's why they wax the boards and wax the sleds and whatever else to get the smallest coefficient of kinetic friction possible, okay? Wax wood on dry snow, not nearly as good, okay? Wet snow would be better, dry snow not as good. Metal on metal, when you're lubricated, meaning you got an oil film or something like that there, look at what you dropped it to. Ice on ice, even more so. Okay? Teflon on Teflon, that's the non-stick surface on pans they used to use. They still use it for some things. That's pretty low too. Y'all know what these are? Synovial joints in humans, especially if you're fairly young. Very, very low, which is very, very good. Now you get a little bit older and lose some of that cartilage, or your lubrication isn't good and stuff. You can get sort of stiff in the joints, right? Okay, now these are approximate values. Now those are your use of Ks when they're in motion. Boy, if only we could get our snowboards to be that good. Okay, I'm not sure we could control them. Okay, now this is going back to applications, I think. So let's stop that. That was all they say about kinetic friction. Now there's several other things that the book does. They talk about the normal force. We've already done that. Okay. They have some other scenarios here. I'll let you read them. They're pretty straightforward. They do the elevator problem here that I'll have to wait and see if they're going to do later. Okay. And they do this problem. Okay. All right. Let me see if they do that one later as well. Yeah, I think they will. So we'll hold off that one for a bit. Okay. All right. That actually, the way they have it here, this is static friction. So let me go back and let's talk about static friction. All right. A few things first at the very beginning. The force of static friction is generally greater than the force of kinetic friction. Okay? Now I have been periodically today pushing on this desk, right? Sometimes I get it to move and sometimes I don't. Okay? So I'm going to push, and the friction that's resisting my motion now is static friction because it's not moving. But when I finally push enough, then it goes, and it goes pretty quickly, right? Why is that? Because the coefficient due to kinetic friction, the force due to kinetic friction is usually less than that of static friction. So I was pushing the same amount. When I finally pushed enough to break that static friction, then it moved easily because the force due to static friction is generally more than that of kinetic friction. Yeah. Okay. That's sometimes why in the cartoon someone pushes and pushes and pushes, and when they finally break free, they fall down here. That's what's going on there. It's not just a cartoon. The coefficient of friction, mu, depends on the surfaces in contact, and we saw that in the slides. Metal on metal is different from wood on metal, is different from wood on wood, and glass on glass. Okay. The direction of the frictional force is always opposite to the direction of motion. It's always trying to retard your motion. Okay? The coefficients of friction are nearly independent of the area of contact. That may seem a little surprising, but they're nearly independent of the area of contact. Okay? Now, more about static friction. Static friction acts to keep an object from moving. Okay? Here was our trash can problem, but this time we're trying to pull on the trash can, but we can't get it to budge because our force is equal to the force of static friction. Of course, the normal force and the gravitational force that are equal and opposite is certainly not flying off the concrete or sinking into the concrete, so it's not doing anything vertically. You're trying to get it to move horizontally, but as long as your applied force is less than the maximum static friction. Here's the thing about static friction. It varies. If I push a little bit, it pushes back a little bit. If I push harder, it pushes back harder. Until I reach that point of maximum static friction, then it moves. And then I don't have to push as hard. Okay. So the static friction force actually does vary. As F, your applied force increases, so does the static friction force, up to a point. If F decreases, so does F sub S. Okay? So F of S is always less than or equal to mu sub S times N, because this is always your maximum static friction. So whatever you're experiencing is going to be less than or equal to the max. Okay? It says the equal sign only for impending motion only. That's only when you reach that point where just before motion begins, that's when that becomes an equal sign. You forget about the lesson. So what this means, here's how we do it graphically. As long as you apply a force, they haven't labeled their graph too well. If you apply the force, your applied force is here, your static force is here, okay? You apply a little, the static force is a little. Apply a little more, static force is a little more, okay? Up until you reach this, what they call the static region goes up until F sub S max, the static friction maximum. Past that, you get kinetic friction, okay, and it starts moving. But it's static up until then. All right, then we've already hit that slide. This is then combining the two graphs together, okay? Static friction is usually greater than kinetic friction. So what happens when you do get motion, then all of a sudden you get when you do pass that S max, then F sub K is less than that, so you have pretty rapid movement, and then you steady in at a fixed force there. Okay, so this is the graph that we describe that. F sub S max is usually greater than or equal to F sub K. Okay, in this way you keep increasing force, increasing static friction until you reach the place of maximum static friction, and then once you exceed that with your applied force, then suddenly it takes off, and now the kinetic friction is less than static friction, but you're pushing at a greater force here, so you're moving it, accelerating it actually. Okay. Now let's look at the comparison of the two. Steel on steel, U sub S, or the coefficient of static friction, considerably greater than the coefficient of kinetic friction. Aluminum on steel, about the same difference. Okay, copper on steel, again, about the same difference. Rubber on concrete, static friction, 1. Okay, that means whatever force you apply, you do that. It's only when you're moving it's a little bit less. Okay? Wood on wood, it may have a very little change here or a much greater change. Glass on glass, static can be quite large, but once it's moving, it's not as good. I can't think of many examples of glass on glass, but I guess maybe others can. Waxwood on wet snow, it improves a little bit. They don't even give waxwood static friction on dry snow. I don't know what that means. Okay. Metal on metal lubricated, static friction a little bit greater, but then once you have kinetic friction, it's even much less. Ice on ice. That's one reason sometimes it's easier to get going on ice than it is to stop on ice. Okay. Because when you're getting going, you're going against static friction. When you're trying to stop, you're already in motion, so it's harder to stop it. Teflon on Teflon, that case is very little, if any, change. And your synovial joints in humans, maybe that's why when you first get up to move, it's a little stiffer than once it's moving. Okay. Now, all right, I think we've pretty much hit all of those topics okay. Now we're doing, this is the example in the text, I believe, yes, on page 97. Okay. What we have, a block on a slope. Okay? This block on that slope, it has a mass of 4 kilograms. So the mass here is 4.00 kilograms. It's the mass of the block. Okay? Rest on a slope that makes an angle of 30 degrees, so the theta here is 30.0 degrees with the horizontal. If the coefficient of static friction between the block and the surface it rests upon is 0.650, okay, so they don't have that anywhere here, the force due to static friction is mu sub s times your normal force, okay? And this mu sub s here is 0.650. 0.650. Now, if you look back at your table, that looks like maybe about something close to aluminum on steel. It's the only thing I see that's sort of close to that. May not be, but something like that. Okay. What I asked you to do is calculate the normal force. So this is the first thing we're asked to calculate. What is the normal force? And again, what's the normal force? The perpendicular force to the surface. Okay? Now, because we're assuming the block is not going to fall through the surface, nor will it fly off the surface, so we're going to assume that this normal force is the same as this component of the weight. The only force downward here is the weight. The only force downward. You're not pushing it, anything else, this is the only force of the weight. One component of that force is down the plane, the other is perpendicular to the plane. This part that's perpendicular has to equal that normal force. Third law. Okay? No, second law, because it's not accelerating into or away from the plane. That's second law. So what we have to do then is break this gravitational force, the weight, into two components, down the plane and perpendicular to the plane. Now here you have to do a little bit of head scratching maybe to get this. Okay? If this is the angle 30 degrees, and this obviously is 90 degrees, that makes this angle up here. Anyone do that? The angle here is 30, and that's 90. What does this angle have to be? 60, of course, because in a right triangle or any triangle, the sum of the three angles have to add to 180. In a right triangle, you know this one is 90 already, so these two have to be complementary. This has to differ by 90, so 30 and 60 are 90. So this is a 60-degree angle, okay? Now, if that's a 60-degree angle, that means the angle over here is also your 30, because this also makes a 90-degree angle. So this theta and that theta are the same. So the component downward here is the adjacent side to this angle. That's the hypotenuse of that angle, because there's your 90 degrees. So the cosine of this angle will be the adjacent side of the hypotenuse. So the hypotenuse is mg. So mg times the cosine of theta is going to be this component here. And that's negative. N will be the positive value of that. Now, the reason that's negative is that G is counted as being negative. Okay? So this right here is going to be minus mg cosine. Let's go on and plug in our values. We don't have enough room to be able to afford too much. I didn't have to erase the equal sign, but this would be minus, the mass is 4.00 kilograms. The g is the acceleration due to gravity, 9.8, we'll call it 9.80 meters per second squared, times cosine of 30 degrees. Does anyone happen to remember what the cosine of 30 degrees is? Second? 0.87 is the value, is the approximate value. The exact value is square root of 3 over 2. Remember your trick? Square root of 3 over 2. Okay, which is about 0.87. So this right here would be the square root of 3 over 2, or 0.87. Okay. So that's going to give you your component of your weight perpendicular to the plane, which will also be your normal force, only that will be positive because it's upward. So let's see what we can do. The 2 will go into 4 twice. So if someone has a calculator, and 2 times 9.8 would be 19.6. So 19.6 times the square root of 3. See what you get. 19.6 times the square root of 3. A little say? 33.9? Okay. So we'll call this negative 33.9. What units would that be, you reckon? Newtons, because kilogram meter per second squared is a newton. Okay? If that's the component of the weight perpendicular to the plane, the normal force will be the positive of that, because there's no motion here. They exactly balance each other out, so this will be a positive 33.9 newtons. And by the way, they've oriented their coordinate system so x is down the plane, y is perpendicular to the plane upward. So that's why it's a positive value. 33.9, is that what you said? Is that the answer you gave me, 33.9? Okay, I want to make sure I wrote it right. Okay, so that is A part. The normal force, 33.9 newtons upward. Okay? The B part, the maximum static frictional force. Well, the maximum static frictional force will be mu sub s times that normal force. Well, that would be 0.65 times that 33.9. So if you got your 33.9 on your calculator screen, multiply it by 0.65. Say that again. 23? Is that what you said? 23.1 newtons? Is that what you were saying? Okay, 23.0, 22. Okay, now that's different, okay? 22.1. That would be 22.1, wouldn't it? If I understood. Okay, I got it. I can't hear well. 22.1 newtons, okay? That would be the maximum static friction up the plane, resisting the motion down the plane, okay? That was the B part, 22.1, okay? The C part. The actual static friction force required to prevent the block from moving. Well, that would be the maximum. So that should be, wait a minute. The actual static friction force required to prevent the block from moving. Okay. All right. Okay, we got that. Actual static friction required to keep the block. No, to keep the block at rest. I was reading it wrong. No, it's the same thing. From moving at rest, same thing. Okay? Now, I think what they're getting at here is, let this enter the picture. Okay? The first one is the maximum static frictional force. Okay? That's based on the interaction there. But this is saying the actual static friction force required to prevent the block from moving. Okay? And I think all that's getting at is to see what this mg sine theta is. Okay? Yeah, that's what they're looking for. Okay? And that would be mg, didn't we just do that? No, we really didn't. So this will be 4.0 kilogram times 9.80 meters per second squared times the sine of 30. Does anyone know what the sine of 30 is? Oh, you shouldn't need to use your calculator. 1/2, exactly, 0.5. So multiply that by, well, let's just do 1/2, okay? Sine of 30 is 1/2. And that way, again, I'll do the 2 into 4 and make it 2, so that would be 19.6 newtons, okay? That says the actual static friction force required to prevent the block from moving, okay? So, the D part says, will the block begin to move or remain at rest? This is the actual force pulling down. The maximum this way would be here. So yeah, it just sits there. It will not move down the plane. Okay? The block remains at rest on the slope. Good deal. Does that make sense? Their wording on the C part was, I see what it means now. The actual static friction force that it experienced from its weight is what it should say. Okay. Let's look at Quick Quiz 4.5. If you press a book flat on a vertical wall, I hate to use my book because I'm afraid my papers are going to fall out, but I'll do it. I don't want to damage that, so I'll take that out. Okay. Let's go back and read the whole question. If you press a book flat against a vertical wall with your hand, in what direction is the friction force exerted by the wall on the book. That's what the tension is. So I press my hand against the book on the wall. Okay? The question is, in what direction is the frictional force? How did it read? Does anyone have your book open? Nobody. Get the question right. If you press a book flat against a vertical wall with your hand, in what direction is the frictional force exerted by the wall on the book? Any ideas? Let me read the options to you. Sorry. That's why I wanted to use some other book. Downward, upward, out from the wall, into the wall. What's the frictional force? Downward, upward, out of the wall, into the wall. Second? Okay. Out of the wall would be the normal force. Because I'm pushing into the wall, that's the book on the wall's pushing back this way. What way, here's the key to it. What way would motion be if it had motion? Down. So what way is frictional force? Always opposite the motion, because frictional force are resisting motion. So that would be up the wall where you drive. No, that's something else. Okay. All right. Now, I've lost the page. Here it is. Yeah. Okay, there it is. That would be B. 4.5 should be B. 4.5 is B. Good for them. They got it right. Get back to the right page here. I hated to use my book. All right. Now, here's some more quick quizzes. Not too quick, are they? Or we're not. Okay. A crate is sitting in the center of a flatbed truck. Got it? As the truck accelerates to the east, okay, the crate moves with it and doesn't slide on the bed of the truck. In what direction is the frictional force exerted by the bed of the truck on the crate? Okay? The truck is accelerating to the east. The crate moves with it and doesn't slide on the bed of the truck. In what direction is the frictional force exerted by the bed of the truck on the crate? A, to the west. B, to the east. C, there's no frictional force because the crate isn't sliding. Okay, A, you said to the west. Okay? Now, let's imagine the C part was true. What if there was no frictional force? In other words, you had synovial fluid between the bed of the truck and the crate. And the truck moved this way, what would happen to the crate? Yeah, okay, it would stay right where it was, but it would seem to be moving that way. So, since the motion would tend to be that way, friction always opposes the motion, so that would be to the east. Since the truck's moving to the east and brings the crate with it, because the crate would normally move to the west relative to the truck, the frictional force must be to the east as well, which was B. 4.6B, sure enough, 6B. Now, 4.7. Suppose your friend is sitting on a sled and ask you to move her across a flat horizontal field. You have a choice of pushing her from behind by applying a force downward on her shoulders at a 30-degree angle below the horizon. Okay? And if you have your books, that would be the A picture at the top of the margin there. Okay? B, attaching a rope to the front of the sled and pulling her with a force at 30 degrees above the horizontal. Which option would be easier and why? Okay? I'm going to use the chair. Okay? I'm going to push down with 30 degrees, or I'm going to pull up at 30 degrees. Which would be easier? Okay, here are the options. Pushing her from behind by applying, wait. Oh, no, those were the options. Which option would be easier? Why? A is pushing downward and B is pulling upward. So which would be easier? A or B? Okay. What are you trying to overcome? Frictional forces. Because the force you're going to exert is the same, pushing or pulling. So the difference is the frictional force, if there's a difference. We don't know that either. Okay? Now, if there's what is the frictional force equal to? Okay? Here we have it right here. Mu times the normal force. Now this is going to be kinetic, not static, but it's mu times the normal force. It's not going down the hill. This is horizontal. There's the formula for it. Mu times the normal force. Mu is the same. Okay? Not changing because the surfaces are the same. So what's the normal force? The normal force when I push, okay, she's sitting in the sled and I'm pushing. Now I'm pushing with this. I've got one component this way, but the other component that way. So there are actually two forces pushing down on the chair. Her weight plus the component of the force that's down. Those two have to be balanced by the normal force up. So that would make a greater normal force. That would make a greater frictional force. Whereas when I pull like this, her weight is still down, but because I have a component pulling upward, that decreases the normal force. Because there's a force in this direction, and the normal force would be decreased. So the B option, attaching the rope to the front of the sled and pulling with a force above the horizontal, reduces the normal force, therefore reduces the frictional force. And that was the reason why. Okay? Let's see how they did in the back. 7 should be B as well. It was, by exerting an upward force, upward component on the sled, you reduce the normal force on the ground, and so reduce the force of kinetic friction. Very good. Does that make sense? All right. Now we're going to look at tensional forces. Okay. Now, that was what I think we were looking at. Nope. Where was it? Yeah, here. I think that's what we're talking about. Now, they do a few more cases here than what we did. Okay? But that's all we've got on this slide set. You can read the book and get a little better understanding in dealing with the tensional forces. Then we're ready for applications of Newton's laws. Okay? And we've already gone over these assumptions, so we won't go over those again. Let's see if we can get, if I can find, because here again we've got our slide set isn't matching the text very well at all. I haven't said anything about free body diagrams yet, so okay, but here's where we got it now. I see that they're doing it, but I just can't see where they've introduced it in the text. Sorry about this. I need to get the... I guess this text just doesn't even bring up free body diagram. They use them, but they don't say anything about it. First place I see it used is on case 4 on page 99, but they just do it. And I can't see where they do this. So let me talk a little bit about free body diagrams. Now, here's a guy pulling really hard on a big old crate. Okay? Now, the magnitude of the force as he's pulling on a rope, that's the tension here that he's pulling on that. That's what is being exerted here. The magnitude of the force T is the tension acting on the box. So we're not talking about him, we're talking about the rope acting on the box, T. The tension is the same at all points along the rope, whether it's here or here or here or here. All points along the rope is the same. That's what we talked about before. Now, since this we assume is a level surface here, then the normal force and the force due to gravity, which is the weight of the crate, those are equal and opposite. If they weren't, the crate would be crashing through the surface or flying off the surface. It's doing neither, so these two are equal and opposite. The tension's there, and this is your free body diagram. Rather than drawing a crate and the guy pulling on the crate and all those things, treat the crate as if it's a single point. Now that was in a slide earlier. A single point, and on that point put all the forces. The gravity's pulling down on the crate, there it is, F sub G on the point. The normal force is pushing up on the crate, there it is, in it, okay? The tension is pulling to the right on the crate, even though it's up here, these are down here, doesn't matter. Make it one point and the tension is that way, okay? And have your orientation, your coordinate system identified. That's going to be X, that's going to be Y. Up is Y, horizontal is X, okay. That's all we're doing with this, is just the illustration of it. And that, by the way, was on page 100. Okay. Oh, wait. All right, sorry, I missed this slide. This I should have talked about before that. Free body diagram is a diagram of all the forces acting on the object, but you identify the object as a single point. You must identify all the objects acting on the object of interest and choose appropriate coordinate system. If the free body diagram is incorrect, the solution likely will be incorrect. So there we've done it for that guy pulling on the crate. Makes it a lot simpler. Easier to draw too. Okay? Only forces acting directly on the object are included on the free body diagram. Reaction forces on other objects are not included, okay? Because reaction forces are always on other objects. The reaction force do not directly influence the object's motion. Only thing that affects the object's motion are the net forces on the object. Here's what they are. This is TIPS 4.7, and that was what we're talking about here. I was looking in the text, not in the margin. Sorry about that. All right, so here are our problem-solving strategy. Bottom of page 100, top of page 101. Newton's second law. Problems involving Newton's second law. Read the problem. And I would say more than once. And as you've noted when I've been doing these, as I read the problem, I'm writing down the pertinent facts. Like number 2 here, draw a picture of the system. Fortunately, on the last problem we did, they drew the picture for me. Okay? I would read the problem, draw the picture, go back and read the problem, and identify, okay, well, when you draw the picture, identify the problem of interest, indicate the forces with the arrows, and guess what? When I'm drawing the picture, does it have to be a crate? Does it have to be a sled? Does it have to be a car? No, you can do a free body diagram, okay? Just do a point that represents that. You might want to do both, but the key is identify those things. So like I said, since they had already drawn the picture, I'm going to identify the features given in the problem with the picture. That's labeling all the forces. And use sort of standard labels. You could use weight as W, or you could use it F sub G, whichever. If you're doing friction, do little f, that's standard. Static friction, little f sub s. Kinetic friction, little f sub k. Normal force, n, always small n, and of course they're always vectors. All forces are vectors. So use the labels that bring to mind the physical quantity involved. If F sub G speaks weight to you better than W, use F sub G. If the book talks about the force due to gravity and you want to call it that, do it. But just know that's also weight. Okay? Label your forces. Draw the free body diagram. So they're saying draw the picture, then draw the free body diagram. Probably a good idea. If additional objects are involved, draw separate free body diagrams for each object. Choose a convenient coordinate system for each object. When you're going down a plane, make your X down the plane, your Y perpendicular to the plane. Even though they're not horizontal and vertical, that's the most convenient. So you can adjust your coordinate system to fit the problem. Apply Newton's second law to each of the forces and to your net forces. The XY components should be taken from the vector equation and written separately. Solve for the unknowns, especially if one of those unknowns is answering your problem. All right. Now, this is 4.5 in the old thing. It's 4.61 in the new edition. Objects at equilibrium. Okay? What's that? It is time. So that's where we'll start next time. Okay? Objects at equilibrium. Let's see if there's some things you can work on before next time. We've still got to do accelerating. Then we'll do two body problems. Thank you. And we don't have much more to go. Okay, so my guess next time we will be finishing topic 4. Then we'll probably go on and start topic 5. Okay? And topic 5 is, goodness gracious, energy. Okay, thank you. And then when 3:30 rolls around, 3:30 rolls around, so we'll only go for an hour and a half. When 3:30 rolls around, we'll stop and we'll do the lab from topic 4. And I'll also give you the, I'll give you the test on topic 4 at the same time. Good deal. Have a good weekend. Working on those research papers, right?
Do you think we're going to get to the lab next in 202 today?
Say this again.
Do you think we're going to get to the lab in 202 today?
Let's see. How far did we get last time?
Not far.
Okay.
We did the lab last time.
Oh, we got, yeah, but we got to 7.4. Good deal, thank you.
17.4?
Yeah, 17 point. We got into 17.4, and we just have energy and power. Well, wait, there was one page on temperature, variation, resistance, not much. Energy and power. Superconductors. Electrical activity of the heart, which is just an illustration. I think we will. I think we'll finish in an hour and a half, and then we'll be ready to do the lab and the test.
And is there any way that I can get the test for next week ahead of time, because I'm not going to be here next week? I already told you.
I don't know how far we're going to get. You need them tonight?
I mean, if possible.
Okay.
So I won't be too behind when I get back.
Okay.
If I can get them,
Yeah.
at least maybe the next.
On both classes?
Yes, sir.
Okay.
If possible.
Okay, I know. Hey, I think I've got them made out. I don't have them run off yet, but I've got to project. In this class, that will be
Maybe
the
test 4 and 5.
yeah, test 4 and 5, and in the other class, I think that'll also be it's 4 and 5, will it?
Mm-hmm.
Okay. So let me do. I know I've got one runoff for the next class. I don't have the one for this class. I don't think. I have to look and see. And then let me look and see.
Okay.
I've got to go find those because I know I brought that up. Yeah, okay. I don't have it run. Well, I have one runoff, but
Because I don't want to be too behind to have so much work to catch up on.
okay. All right, I need to end this.